a compression-resisting core of water or watery material or biological tissue that's 90% water or something like that. There's a squid whose mantle looks that way, and the mantle with the mantle cavity in it. There's a snail whose actual foot is hydrostatic, an earthworm, quite a substantially hydrostatic thing, a caterpillar, buttercups and stems are partly hydrostatic. This is from a textbook I wrote a chapter for. There's a blank here. The blank is a penis. You see, they've got to sell this thing to fruit school boards. And they're also a tensile membrane wrapped around a compressed liquid and achieving a certain amount of stiffness thereby. In fact, my colleague Steve Wainwright has shown, in fact, that sharks are built this way. That's why sharks can get away with such crummy bones. They have very strong, very tensily resistant skin, and when they get started swimming, the internal pressure goes way up and it keeps them stiff. I mean, really what a shark is, it's a shark-shaped balloon with teeth. On the other hand, no hydroskeleton is really all that stiff. On the other hand, of course, its stiffness is adjustable, depending if you put muscles in the outside and you contract the muscles, you can decide how stiff it's going to be, or in fact, you can pump up the liquid in some cases, as in penises or the tube feet of echinoderms. Now, someone in another department, Duke, has commented that tin cans, cylindrical, are really phallic symbols, part of the enslavement of women and so on and so forth, about which he carries on at great length. Now, to say that tin cans are phallic symbols, I think recognizes a very, very real and important element of commonality between the two. They are both fluid-filled, hydrostatically supported cylinders. I don't think it has anything to do with symbolism. It's just a basic sort of physical relationship going back to Laplace's law, which we talked about earlier. And you'll notice, reminding us of Laplace's law, that these things are basically, although you don't see it up there on the foot of the snail so easily, these things are cylindrical, getting back to that point made earlier. Well, we've carried on some about materials. Let's turn at least briefly to devices. See, we're getting on here, making our way through this. Machinery. Stuff in nature tends to go back and forth. Stuff we make tends to go round and round. There are wheels and axles in nature. It isn't as if nature never makes them. There's the bacterial flagellum is known to be a true wheel and axle. So the wheel and axle is actually of considerable antiquity in nature, but it's pretty rare. I believe that the only true example known is the bacterial flagellum, and the people have actually been looking around for them for quite some time. On the other hand, we sort of like wheel things. We have a whole culture of wheeled vehicles, and there are all kinds of wheels inside them, and wheels and wheels, and so on and so forth. But as my friend Michael Barbara pointed out once in a kind of a neat paper he wrote in American Naturalist, he said wheels are lousy. These wheels work best on prepared surfaces of the sort which our technology makes, but you don't find out there in nature. A wheelchair even works terribly on shag carpet. It's virtually immobilized by any give in the surface. And if the terrain is at all bumpy, you need very large wheels because the radius of curvature of the wheel has to be greatly in excess of the radius of curvature of the bump. If it's to go over it or deal with it in any way at all. That's why the prairie schooners had to have such big wheels, enormous wheels on them, and you couldn't get them across the prairie with 13-inch tires, or they just would not have worked. Nature, you see, then in Mike's view at least, simply avoids the whole issue by not making wheels, by making very much more versatile, if somewhat less mechanically efficient, reciprocating appendages, or at least less mechanically efficient on optimal surfaces. And so we have organisms built like this one, without evident wheels, but with the rapid development of reciprocating appendages with which it can get around alarmingly well. So, 2 points. First, wheel and axles would rather be in sort of an evolutionary discontinuity, and secondly, wheels may be rather overrated, really, for terrestrial carriage of the sort that nature would most likely encounter. Particularly if you, as we recall, the average organism is a millimeter to a centimeter long, and for something that size, the world looks pretty bumpy. And if it's pretty bumpy, then wheels don't work for them. Well, here's some levers. First, second, and third class levers. Never mind the first for the moment, it's there just for sort of completeness. The second class lever, you've got the pivot at one end, the load in the middle, and the effort, that's you heaving on it, at the far end. The third class lever, you pull on it in the middle, the load, say in this case you might imagine the weight, is out here. In the second class lever, you don't take as much effort, but you have to move it further. In the third class lever, it takes a great deal of effort, but you don't move it as far. So there's no real problem with energy conservation and things like that. Now, we like second class levers, and nature likes third class levers. Here's a second class lever. It's a nutcracker. And if you think that's the only one, we just dipped into our kitchen drawer and found a whole bunch of other second class levers. They're just all over the place. On the other hand, if you look in nature, you find the third-class levers. Even when you want a fair force development, this is a lion skull. I marked with a red pen, a red something or other. I don't remember what it was. Marked with red the pivot point. I put a piece of paper in there for the main masseter muscle, and say you're chomping down with those teeth. You've got pivot, effort, load. Third-class lever. In this case, and we've got a third-class lever, here in our biceps muscle, the weight on the end, the effort where that biceps muscle is, and then the pivot over facing B. Pivot, effort, load. In fact, very often in places like our kitchen, what goes on is that we use second-class levers like a nutcracker to reverse the effect, the action of nature's third-class levers, our bones and muscles. You see, what's going on is that muscle is a wonderful force-producing device, but it's a short-distance machine. A 10% contraction, 10% shortening is a pretty decent working shortening for a muscle. And yet we want a forearm that swings, not some small angle of 10 or 20 degrees, but which will swing close to 180 degrees. And so we have to somehow amplify the motion, and we do that with a third-class lever. The predilection of our technology for second-class levers is perhaps best seen in a bit of terminology that you've probably all heard, the term mechanical advantage. That is the measure of how secondy the second-class lever is, because that's a measure of how good it is. You see, we value the thing, it's got a mechanical advantage at 10. That means, 10 times as much motion, well, the other way, I'm used to thinking of these organisms. But yeah, you move something 10 units and you get out one, but you need only 1 unit of force, and you've got 10 units of force applied to the load. And that's a real good thing. It's not a mechanical advantage of 10. If it had a mechanical advantage of 20, it would be even better. Well, finally, because I'm going to quit my comparisons after this one, rotation. Our engines tend to rotate. In our technology, there's an electric engine, or they tend, in their deepest in their bellies, to expand, as in that gasoline engine on my lawnmower. Whereas the engines in nature, there's muscles, tend to contract or shear rather than expand or rotate. There are some expansion engines in nature, various osmotic engines and so forth. It may be that expansion engines really demand stiffer structures than nature commonly uses. It's not at all clear why. But one consequence of this difference, I didn't say I'd explain it all, one consequence of this difference is that it is exceedingly hard, damnably awkward, to build prostheses of bits of organism involving muscle. Because muscle is a kind of engine which turns out to be not so much better or worse, but just enormously different from any engine that we have available in our technological armamentarium. Well, so that was 11. Then I get a couple of minutes to moralize. Well, before that, I've got to say, there are other contrasts. One can go on, and of course I look at this list, there's still others. Whether we want to read all of these. Right down to the fact, nature is wet, and our technology is dry. Nature's bricks are microscopic, our bricks are macroscopic, and so forth. Now, a couple of points, though, in conclusion. This comparison of two technologies is nothing new at all. But the usual bias has been to look for parallels and convergences with a goal of making useful things by copying nature. I mean, nature's been at it for billions of years. Look at all that wonderful stuff out there. Hey, we can copy it and make something just wonderful. It's a kind of wonderful residual pantheism that we get. And once in a while, it works. Velcro, copied by a Swiss engineer after he came back from hiking around, and there were some plant burrs on his pants, literally. And it's wonderful stuff. But often it's just a brave sort of promise. There is something, a kind of a maple seed, which is acting as a parachute of sorts. And this was sent to me by someone who found it in a magazine, and it was published about 1949. So we've had plenty of time, and they're still not filling the sky. And one sort of suspects that the artist, might have indulged in the sponsored product. Now, worse than just a brave promise, though, sometimes it's an absolute disaster. This is a book on. If you read German, you can read the title. And for me, it's easy because it's got my name embedded in it. It says, Bird Flight is the Basis of Artificial Flight, and it's by Otto Lilienthal. And while it says 1910 here, which you can't really read, the original version was 1890. Lilienthal did a wonderful study of bird flight, vastly superior in every respect to anything that had been done up to that point. And he used this as the base, as the information for building what we would now call hang gliders, but which he was using to work toward flight. And there he is. And the result of which was that he killed himself in one of these contraptions, because birds are exceedingly unstable. They've been around for quite a few million years, and they have cooked up nervous systems which can deal with the instability and buy them all this wonderful maneuverability, and they make very poor models for building practical flying craft. So Lilienthal got in trouble. The Wright brothers succeeded in part because they built something that looked extremely unbird-like and paid great attention to the problems of stability. They worried incessantly about whether a human would be too disoriented to run any controls, and designing some control that was so simple that a human, in a terrible state, up in the air with the thing doing crazy things, we could actually be able to control. They worried about the non-avian aspects of the flying machine. Well, I'd argue that what's impressive about the contrast is the range of difference between natural technology and our own. Truly magnificent. And I think it's a great mistake to look at the contrast, to look at nature, even though I'm a biologist, deep in my heart of hearts. But it's a mistake to look at nature and bash technology, bash human technology. We do really very well. And nature doesn't do half so well as we would like to believe sometimes in our biological kind of nature worship. Nature's grand, but she's not omnipotent. She's constrained by all sorts of problems, all sorts of inabilities to handle discontinuities, by a system, an evolutionary system that finds it very hard to do any fundamental innovation. It can only tinker a little bit here and a little bit there, testing things fairly immediately for utility and not planning ahead, not making hopeful monsters, as I think somebody said, I don't know, Goldschmidt or something, or maybe it was said about him. And evolution is constrained by developmental problems, where she builds a system and can't easily suspend function when she wants to do a little renovation of it. There are some attempts, there are things like pupae and insects, but by and large, nature has to do the equivalent of changing a motorcycle into an automobile while providing transportation the whole time. This must be enormously constraining to what things can actually be contrived. So nature isn't playing on a completely ideal surface. And human technology has really come a long way in a short time. The devices we've contrived, I think, are generally sensible, given the materials we have available. Although sometimes it takes us a little while to catch on. I mean, the early iron bridges looked like wooden bridges, and the early steel bridges looked like iron bridges. But, we catch on eventually. And our technology is one that works well for our size of operation, for our scale of humans and the things that we make. Now, this isn't to say that one shouldn't compare the two technologies, as of course I just have begun to sketch out for you. I think it's enormously useful in all sorts of ways to compare the two. What you gain, though, is not specific guidance on how to make better widgets or flying machines, mostly. What you gain is a general perspective. While we didn't learn to make airplanes by copying birds, if birds and other animals didn't fly, would we have ever imagined that something so improbable was in fact practical? I think not. At least not right away. If birds didn't fly, I wonder if we ever would have tried. So if we can't make better widgets with this comparison, why do it? In fact, why have science at all? And I think the whole answer, just to make a final sort of polemical pitch, is the same answer as why have art? What you're really wanting you to do, in fact, is to get that general perspective, to have some more penetrating, insightful view of the world, where for every item, as mundane as they are, one can go out and look at them and see them, in their full both biological and aesthetic and functional glory. Well, maybe that's a little bit too pretentious. I should quit while I'm ahead. Thank you very much. Stuff you saw, a lot more about those leaves and things like that. People have comments, suggestions? Yes?
I've got one. We talk about metals, and you kind of have some possibilities on why nature has produced what we have. And you're not really sure, but maybe some other things you consider to be one of the coefficient expansion when we heat up the one organism, the big one that suddenly has to, go on a sunny day and gets even longer.
it's so hard to guess what might be, really involved. I tend to think that all of that high thermal conductivity puts a wonderful advantage, as could the electrical conductivity. I mean, we do build nerves, but they're really, again, they're lousy. Nerves are terrible. The conduction speeds are so low. We have measured meters per second. We only get away with building nervous systems by building the most massively parallel processors one could imagine to get any computing power at all. So maybe, again, it's a metal nerve would be, again, but you can argue it about, it's hard to argue about worlds that don't happen. That's the stuff of wonderful science fiction. Other, yes.
On flat surfaces, you tend to talk about them in relation to structural staticness. What about inverted locomotion, fluids, and also air, wings, fins, things like that?
They're used, and they seem to be relatively tricky to make. All sorts of odd bracings and so forth. Occasional uses of bat wings, membranes, where if you take pictures of them in flight, they do what they're supposed to do, and bows all of the expected problems arise, just as they would for an engineer trying to make a flat surface. I think at some stage airplane wings went from flat but membranous curved surfaces to sort of solid things that we have now, which you had some place to put your stiffening members. I think the aerodynamics wasn't dramatically improved, but the mechanics were helped. We in nature face the same basic difficulties. Fossils will apply equally. Fishkins have to have all these rays and still deflect. Tricky one way or the other, I think.
What happened to the dinosaurs?
I'll tell you what happened to dinosaurs. The dinosaurs were living in the late Mesozoic, and the vascular plants came along and displaced the ferns. And the dinosaurs that have been eating ferns for a long time, and they were very used to eating ferns. And as anyone who's ever eaten ferns know, ferns have a very strong purgative effect. And the world suddenly deprived of its ferns. That's not, first of all, I didn't mean to insult you. It's not original. It was suggested many, many years ago, somewhat tongue in cheek. But I don't know. I actually reviewed a paper not too long ago that talked about the Earth's gravity changing and the practicality of building large animals becoming greatly reduced. But the evidence was not there. And it's been suggested from time to time, and nobody's found any particular evidence that the Earth's gravity varies anywhere near enough to make a difference. I don't think it's straight mechanics.
Well, if there are no more questions, we have some punch and cookies or something over there.